Good morning. So today we will discuss this idea of data flow analysis, which helps in optimizing programs at a per function level. You recall from the discussion in the last class, we studied local optimizations which work at the basic block level, and we studied two kinds of regional optimizations. One works at the level of extended basic blocks, and the other works at the level of at a level or a region induced by dominator trees. And the next level or the next scope for optimization is at the level of a function, where we construct a control flow graph for a function and try to perform optimizations on this control flow graph. These are called as global optimizations. So just want to summarize. Number one, we have seen local optimizations on a per basic block level. Number two, region-based optimizations. And here we looked at extended basic blocks and dominator tree-based approach. In today's class, we see what are called as global optimizations. And these global optimizations, they are also called as intra-procedure optimizations. That is, they work within the scope of a function or a procedure. So here they work at basic blocks. So here we work at control flow graphs. This is where we work at. So we take a function and we construct a control flow graph associated with that function. And without loss of generality, we assume that the control flow graph has a single entry node or a special entry node, and the control enters the program or the function only through the entry node. And it has a special exit node, and the control leaves the function or the program through that exit node only. Usually it is the case if you think of a function that the control enters only at the beginning of the function. So this is not a problem. But then if you think of the exit node, there can be multiple return points within a function. And we can kind of merge those multiple return points without loss of generality and construct a single exit node through which the control returns from the function. And these entry and exit nodes, they don't have any instructions in them. So we assume this without loss of generality because in given any arbitrary control flow graph, we will be able to transform that control flow graph into a form which has these three properties. That is, it has a single entry node, it has a single exit node, and entry and exit nodes, they don't have any instructions in them. For example, if you consider a function with single if statement. So let's assume that there is a return statement here and there is a return statement here. If you transform this, if you construct a control flow graph associated with this if statement, the control flow graph looks like this. So you will have a basic block in which there will be code for expression, and then you will have a basic block for the if part of the expression, and you will have a basic block for the else part of the if statement. And we can, so you can see that there are two exit points or two return points, and there is one entry point, but the entry node has some instructions present in it. But we can take this control flow graph and transform it into a control flow graph like this, where it has an entry node with no instructions present. Control enters the program through this entry node, and then it enters the code, enters the basic block which contains the code for the expression. Depending upon the predicate that is evaluated at this point, either you go this way or this way. And what we do is we kind of merge the return points at the end of these two basic blocks by adding a new basic block called as exit, and we can put a go to statement at the end of these two basic blocks. So this is how we can take an arbitrary control flow graph and transform it into a control flow graph with a single entry node, with a single exit node, and the entry and exit nodes, they don't have any special any instructions in them. They are empty. Yeah, so this is yet another example of a control flow graph with a single entry point and a single exit node. And you can see that all the instructions in this control flow graph are numbered. And so these are primarily for convenience, but we will use a different notion in order to see what goes in these control flow graphs while doing program analysis. So if you take this control flow graph on your right hand side, so we define what are called as program points. A program point is a marker after and before each statement in the control flow graph of a program. So we have the program point P0 in the entry node, and we have a program point before this instruction, which is P1, and we have a program point after this instruction, which is P2. Similarly, if you look at this instruction, before this instruction, there is a program point P2, and after this instruction, there is a program point P3. And these program points, don't confuse them with labels in a program, because labels, the programmer gives labels, but these program points are, think of them as mathematical structures which we imagine to help us in program analysis. Okay, so they are not really there. These program points, they are not really there in the program. They are not as a part of the program, but we associate a program point to every to different places in our program, that is before an instruction and after an instruction. And labels are different. Like for example, here we didn't put an explicit label, that you can have something like go to L1, and so L1 could be here. So a label is a entity which the programmer defines and uses, but program points are just for our convenience to think about going about program analysis. So if you think of an execution trace, an execution trace is uniquely defined by a sequence of program points. Like for example, if you execute this program, and if the program takes this path, then this path is defined by the sequence of program points P0, P1, P2, P3, P4. So this sequence of program points, they define the execution trace associated with this particular execution run of the execution path of the program. So associated with every execution trace of the program, there is a sequence of program points which can identify the trace. All right. And if you think of a program when invoked, it starts in a certain initial state S0. What is the initial state associated with a program? That is the state of the global variables, the state of the stack, the state of the place where the program counter is present in. So when we start a program, there is an initial state associated with that program. When we talk of Turing machines, this initial state of a program, we can easily associate by by looking at the corresponding configuration, Turing machine configuration. Like for example, a Turing machine starts in state Q naught, and let's say the input tape, it contains a sequence of symbols A1, A2, A3, so on up to AK. This is the initial state associated with a Turing machine. And then, so after this, the Turing machine, so when the Turing machine is in state Q naught, and if it reads A1, it can move that head to the left or right, and then it can replace this symbol A1 on the input tape with an arbitrary symbol. So let's say the Turing machine goes to replaces this A1 with a non-terminal symbol or or a tape symbol A, and it moves its head to the right, uh, and it moves, and the control moves from state Q naught to state Q1, then the configuration of the Turing machine will be like this. So if you think of Turing machines, it is relatively easy to capture the state because the Turing machine starts in some initial configuration, and then it keeps progressing from one configuration to another configuration. As the Turing machine moves from one configuration to another configuration, the internal state in the control, it changes. Uh, and the second thing that happens is the state of the tape, the Turing machine tape also changes. So what happens in a program is very much equivalent to what happens in a Turing machine. So a program also has a state, as the program executes instructions by passing through various program points in the program, the state of the program keeps evolving. So initially the program could be in state S naught, and it can pass through, like for example, the program point P1, and after it passes through the program point P1, it goes through state S1, and from state S1 it may pass through program point P2, and it can go to state S2, so on and so forth. And one important observation is, so a program starts in S naught and it keeps traversing through multiple states, and it can reach a program point P. It can reach a program point P. When it reaches a program point P, the program could be, the state in which the program could be, it need not be the same. It depends on the path which the program takes to reach that particular program point. So for example, in this control flow graph, if you look at the program point P10, the state in which the program is in, let's say the state associated with this program is the contents of the variables A, B, C, D, E, and X. So the value of the variables A, B, C, D, E, and X, when the program reaches the program point P10, it depends upon the path taken by the program to reach that program point P10. And static program analysis techniques, that's what we will be studying in today's lecture and in the next lecture. They would try to deduce properties for a state which hold at a program point Pi, independent of the path taken to reach Pi. Like for example, at program point P10, we want to know whether some variable is a constant or not. Let's say we want to know whether the variable A is constant here or not when we reach the program point P10. Constant means it holds some constant value. Then, so but we can reach in one particular configuration, or if the program takes one particular path, the variable A could be a constant, and if the program takes a different particular path, the variable A may not be a constant. So the answers that the properties that we would like to deduce about the state S of the program. So when we reach program point P10, so depending upon the path taken, so the state of the program could be S1 or S2 because there are two paths here. But in general, if you see there are infinitely many ways starting from P0. There can be infinitely many ways from P0, this program point P0, and an arbitrary program point P. There are infinitely many paths from P0 to P. There are infinitely many paths. And each of these infinitely many paths may result in infinitely many distinct states associated with program. And whatever the property that we deduce about the state of a program at point P, it has to be true for all the states. Like for example, all the possible states in which the program can be in, when the program reaches the program point P naught, let's call it as, this not. So S1, S2, S3. So if you say that when the program reaches point P, it holds this particular property, then that means that particular property should be true whether the program is in state S1 or in S2 or in S3, so on and so forth. We will try to understand this particular idea through multiple examples in today's lecture. Yeah. So now let's consider this problem called as constant propagation problem. So this is a control flow graph. There are no loops in this control flow graph. There is an if then else statement, and there is a program point P here. And the question is, we focus our attention on the variable C, and we want to know at the program point P whether the variable C is a constant. If the variable C is a constant, and if that constant is a unique constant, then we can apply a optimization called as constant folding. We can do what is called as a constant propagation. Followed by that, we can do an optimization called as constant folding. What is constant propagation? So at point P, at the program point P, if you see whether you take this particular path or whether you take this path, so whether you take this path or whether you take this path, at program point P, the variable C holds a constant value, and that constant value is 2. So we can do constant propagation optimization, and we can replace this C with 2. Followed by that, we can apply a constant folding optimization, wherein we know at program compilation time itself that the RHS it contains only, the RHS expression contains only constants. So we evaluate that expression and we will say C is equal to 3. So if there is yet another program path along which the variable C is not a constant, then we will not be able to do this optimization. So this is what we were talking about before, that when we try to argue about the property of a program at a particular program point P, the property should be true no matter which path the program takes to reach that particular program point. So now let's look at one more example. So in this example, so we have C is equal to, again the question is variable C a constant at program point P? And in this case, the answer is no, because if the program takes this particular path, then this becomes a problematic instruction, because the value of C is getting modified depending upon the value of A. So along this path, C is still constant, but along this path, C is not a constant. So we cannot do constant propagation and constant folding for this instruction C is equal to C plus 1. So what is the definition here? If we say that a variable V is said to be holding a constant value C, we say that a variable V is said to be holding a constant value C at a program point if all the paths, please remember, make a note of this, if all the paths from entry to P, from the entry node to P, if they contain an assignment statement V is equal to C, such that V is not redefined after the statement and before the program point P. It is a bunch of words, but I guess you intuitively get the definition here through multiple examples that we have been looking at, and we will look at few more examples so that the definition sinks in. So now we have one more example here. Along this path, the value of the variable c, it's a constant, and the constant value is 2. And if the program takes this particular path, the value of the variable c is again a constant, and it is equal to. So at the program point P, if you ask the question, is the variable C holding a constant? The answer is yes, but unfortunately it is not holding the same constant. Along one path it is holding the constant 2, along another path it is holding the constant 3. So we will not be able to, replace the variable. So we will not be able to replace this variable C with either 2 or 3, because it depends on which path it is taken. So there's a problem here. So how do we solve this problem? So one way of solving this problem is by applying an optimization called as basic block cloning. Basic block cloning. So if you clone the basic block, then what happens is you have 2 copies of the same basic block. And so now, if you ask the question, is the variable C a constant at program point P? And the answer is yes. And the constant value is 2. So we can replace this C with 2 through constant propagation, and then we can apply constant fold. And similarly, if you ask the question, is the variable C constant at program point P prime? The answer is yes, and we replace this C with 3, and through constant propagation optimization, and then we apply constant fold. So how about this this control flow graph, which has a loop in it? So this is an interesting example. Along this path, C holds C is a constant and it holds the value 2, and along this path also C is a constant and it holds 2. But there is a problem here, because the program can actually take this path. It can come to this basic block, and then it can take this loop. It can go like this. So if the program chooses to take this loop, the value of the variable C is getting updated in this basic block. And so after it loops for some time here, and when it takes this path, the value which C takes is no longer a constant, it is some arbitrary value. So in this case, we cannot do, constant propagation is not possible here. So because the variable C is not a constant at the program point. So these things which we are trying to understand through examples, we have to come up with algorithms which can do this analysis automatically, and helps the optimizer or the transformation pass with all this information, and the transformation pass can use this information to do suitable program modifications. So now we will see one more kind of optimization or analysis which enables one kind of optimization. So the optimization is common sub-expression elimination, and the analysis module is available expressions analysis module. The question here is at the program point P, is the expression B plus 6 available? Available means, so we should be able to eliminate that computation. We should be able to, it's a redundant computation, we should be able to eliminate that computation. So if you take this particular path, if you see the expression B plus 6, it is computed here, and along this path, the operands B and X are not modified, and along this path also the operands B and X are not modified. So because of that, the value that we have computed in here, we can use that value to eliminate the computation that is present here. Maybe we can transform this module by saying C is equal to A. I know there are problems here because A is occurring on LHS here. So maybe if you transform this code into SSA form and then try to do available expressions analysis, then we might be able to easily eliminate the redundant computation at this instruction. Or the other way, as we have seen before, is we can say T is equal to A, and we can say, we can transform this code into C is equal to T, where T is a compiler introduced temporary. The second approach is not a nice way of doing it. We are better off if you use a SSA representation of the programs. But let's not get to SSA representation again, because we want to understand a different set of ideas in these lectures. The important idea here is the expression b plus x that is computed at the program point p. That is the conclusion that we would like to make, so that we can eliminate the redundant computation in the instruction that is present after the program point. Now let's look at this example again. So is the expression b plus x available at the program point p again? So if you see, the expression b plus x is not computed in this basic block. It is computed in this basic block here. So if the program takes this path, then it is available at the program point p. But if the program takes this path, then it is not available at the program point. So we cannot say that the expression b plus x is available at the program point p. So that's the conclusion here. How about now? So now it is possible, because whether we along this path, b plus x is computed here, and b plus x is again computed here, so we can eliminate the redundant computation. So same along this path, b plus x is computed, and b plus x is again computed, so we can eliminate the redundant computation. One point I would like to make a note of here is the value of the expression b plus x when we come along this path, and the value of the expression when we come along this path, they could be different. But still we should be able to eliminate this computation. Like for example, let's say at the beginning of this basic block, we have b is equal to 1 and x is equal to 2. And at the beginning of this basic block, we have b is equal to 100 and x is equal to 200. So the value of the b plus expression when we come along this path is 300, and the value of the b plus x expression or when we come along this path is 3. But still, like we can still be able to eliminate the computation b plus x here. Okay, because if the program takes this path, then the value that of the expression b plus x at this particular point is 3. And similarly, if the program comes along this path, the value of the expression at this program point is 300. So yeah, still we should be able to eliminate the redundant computation in this instruction. So now let's look at one more example. So again, in this example, so whether we come along this path or come along this path, the expression b plus 6 is available. So it is important again to note, depending upon the path, the value of the b plus expression could be different, because, but still the computation at program point p, it is still a redundant computation, because if you take this path, so if you take this path, then what happens is the value of the b plus x that is computed here will be reused here. And if we take this path, the value of b plus x that is computed here will be reused here. So because of that, the transformation that we would like to do based on this available expression analysis is still valid. So here is a formal definition for when we say that an expression is available at a program point P. We say that an expression x plus y is available at a program point P if every path from entry node to the program point P evaluates x plus y, and after the last such evaluation prior to reaching P, there are no subsequent assignments to XOR. Again, it's mouthful, but quite a mouthful, but it's important that you go through this definition very, very carefully. You can later on, after the class is over, I recommend you to read this definition carefully and try to understand what the definition says. But now I presume that you got the intuition on when we say that an expression is available. If you take this particular example, so which kind of clears out one particular idea which we didn't see in the previous examples. Uh, if you consider the computation of the expression b plus x here, so b plus x is computed here, and so along this path, the b plus x is available. So no problem, this is a good path. But along this path, it's a problematic path. Why is it a problematic path? Because one of the operands of the expression b plus x is modified in this instruction. So because of that, the expression b plus x is no longer available, because the value of the expression b plus x that is computed here changes at the program point p if we take this particular path, because one of the operands is getting modified. If this tuple is not there, then the expression b plus x is available along this path also. In which case, it becomes a available expression at the program point. But in the current example, where we have the tuple b is equal to b plus c, it is not the expression b plus x is not available along this path, because one of its operands b is getting modified. So this is the intuition about the available expressions analysis problem. Yeah, one more example here, where we have a loop. If you see, the expression b plus x is available along this path, and it is also available along this path if this loop is not taken. But if this loop is taken, then what happens is one of the operands of the expression b plus x, that is x, is getting modified in this tuple. Because of that, the expression b plus x is not available if the program takes this path. And remember, we say that an expression is available at the program point p if no matter which path the program takes to reach the program point p, the expression is still available. Whether it is this path, or whether you loop around this once or loop around this twice, it doesn't matter. So finally, independent of which path the program takes to reach the program point p, the expression b plus x should be available. So here in this case, there are infinitely many paths for the program to reach the program point. Why there are infinitely many paths? Because there is a loop there, and we can, depending upon the input variables, the program may loop many times across this loop, right? So there are two paths along which the expression b plus x is available, but there are infinitely many paths along which the expression b plus x is not available. So we say, when we do program analysis, when the compiler does program analysis statically at compile time, it deduces that b plus x is not available at the program point, right? So now we look into next analysis problem, which is called as a live variable analysis problem. You may recall from our discussion from few classes back, the live variable analysis problem, it helps in identifying dead code elimination, in performing dead code elimination optimization, for example. It will be useful, I think, even in register allocation also, but we will see register allocation in a later lecture. But for the time being, we know that when there is an instruction which involves a variable which is not live on the LHS, we consider that instruction as a dead instruction or an useless instruction, and we let go of that instruction. Okay, we eliminate that instruction from the program. So here, so this is the formal definition of live variable. We say that a variable v is live at a program point p. A variable v is said to be live at a program point p if the value of the variable v at point p is used along some path p from p to the exit node before it is being redefined. So this is interesting in the available expressions problem. So the way we have defined this in the available expressions, we started with the entry node and we considered a program point p, and we say that an expression b plus x is available at the program point p if the expression b plus x, if it is computed on all these paths, not just one path, it has to be computed on all these paths. And not only that, after the last computation of the expression b plus x, the operands, either the operand b or x should not occur on the LHS. So this is not allowed, b or x on the LHS. Okay, so this is not allowed. So this is not allowed. This is a variable x. This means not allowed. Okay, so in the available expressions analysis problem, we are considering paths which are emanating from the entry node to the program point P, number one. Number two, we are saying that no matter which path the program takes to reach the program point P, the expression b plus x should be computed. It should be there on the RHS of some tuple. And after the last computation of the expression b plus x, the operands b or x should not be modified before we reach the program point. Whereas in the live variables analysis problem, the structure of the definition is a bit different. From the program point P to the exit node, look at all the paths. Look at all the paths. So here the qualifier that we use is for all paths, for all. But here the qualifier that we use is there exists. Okay, so this is the qualifier that we are using. So if we say that a variable v is live at the program point P, if there exists a path, in which the variable v is used on the right hand side of some tuple, and before its use, it should not be defined it should not be there on the LHS. Like for example, at this particular point, if v is on the LHS, then this is not considered a valid use. Okay, so this is not good. So we say that a variable v is live at program point P. If there exists a path from P to the exit node, such that along this path, the variable v is used before it is being defined. So after this use, v can occur on the LHS, not a problem. Okay, so something can be there. This is all right. But before the use, v cannot be on the LHS. Okay, so this is not good. This is all right, no problem. So let's look at one more example, and then we will analyze the control flow graph that we have before. So here, so this is the entry node and this is the exit node. We are considering whether a variable v is live at the program point P or not. In this first case, in this first example, the variable v is live at the program point P because along this particular path, v is used on the right hand side before it is being defined. Along this particular path, v is neither used nor defined, so this path is useless to us. It doesn't matter, we are indifferent to it. And again, this path is useless because v is occurring on the LHS before it is being used on the RHS. But there is one path in which v is there used on the right hand side. So we say v is live at program point. Now if you consider this example, so in this example, v is occurring in two paths. It is not occurring in the middle path, but still the occurrence of v in the leftmost path and the rightmost path, it is useless to us because v is occurring on the left hand side. That is, it is being defined, it's not being used. But on the contrary, if you look at the last example, in the last example, v is live because there is a path along which v is used first before it is being defined. So in this path, v is used and defined, but it is all right because v is used before it is defined. So this is good. So this is how this is the definition of the live variables. And so when you are trying to formulate these analysis problems, coming up with the appropriate definitions and getting good intuition behind why we are defining it in such a way is very important. So now let's try to look at this code, this control flow graph, and see what are all the variables that are live at different program points in this control flow. Here is. So one thing we will see, there are how many variables are there? So there are A, B, C, D, E, and X. So we have A, B, C, D, E. There are 5 variables uh, plus X. So we can represent this thing as a vector of as a bit vector. So this bit is associated with variable A. This bit is associated with variable B. This bit is associated with variable C, D, E, and X. So this is a bit vector. Oh, sorry. And so this is a bit vector, and we can represent at a program point P1. Let's consider program point P1. At program point P1, what are all the variables that are live? Is variable A live? So in order to check whether variable A is live at program point P1, we look if there exists a path from P1 to the exit node along which A is used on the right hand side somewhere before it is being defined. So it turns out to be not, because A is defined first. So A is not live, so we put 0. And if you see B and X are live because, sorry, B and X are live because they are used here. And variable C is also not live. How about variable D? Along this path, D is used on the RHS, so D is live. And how about E? E is not live because if you consider this path, E is defined on the LHS, so it is not live. So this is the bit vector associated with the set of live variables at the program point P1. So now let's look at, we will take some random program points and see what is happening there. So now let's look at program point P10. At program point P10, so 1, 2, 3, 4, 5, 6. So again, this is A, B, C, D, E, X. So at program point P10, variable C is live. How about variables A, B, D, E, X? So it is an interesting question whether A, B, D, E, X. If you look at the program text, we are not seeing their occurrences either on the left hand side or right hand side. So we may assume that these variables are not live at the program point P10. But if you think about it, let's say out of these variables A, B, D, E, X, A and B are local variables. So A is a local variable, B is a local variable. That means their scope is within this function. If their scope is within this function, then we can immediately conclude that they are not live. But on the contrary, let's assume that D, E, X are global variables. If these are global variables, then whether they are live or not, it depends upon the particular point from which this function is being called. We may not be, unless we do some kind of interprocedural analysis, we will not be able to conclusively say whether the variables D, E, X are live or not, unless we do interprocedural analysis. But let's say we don't have an interprocedural analysis module available with us, then we cannot just assume that DEX are not live, because if you assume that DEX are not live, we may think like, for example, this statement is a dead statement and dead code elimination state uh, module, optimization module may eliminate this particular statement. But on the contrary, but it may turn out that D is live, and so our whole transformation, it changes the semantics of the program, we will get into trouble. So in the absence of any interprocedural analysis module, we have to safely assume, or we have to err on the safe side and just think that the variables DEX are live. It may not be accurate, but we may have to assume it in the absence of any other information. All right. So we'll just take one more example and then we will conclude today's class. Let's take program point P3, or yeah, let's take program point maybe P4. Let's take program point P4 and see what happens. So we have A, B, C, D, E, X. So at program point P4, one thing we can conclude is variable A is live because we are using A on here. So variable A is live. How about variable B? Variable B is also live because we come along this path and here we are using B. So variable B is also live. Similarly, variable by the same argument, variable C is also live. And how about variable D? So variable D, so we don't, assuming, so let's say if you think D as a local variable, then so it's not available in the program text here. So variable D, we may have to assume D as not available. And the variable E, it is not available, it's not live because it is occurring on the LHS, and same with variable X. So usually at program point P10, when I take this example, I wanted to illustrate one idea, but otherwise for the sake of the lectures that we see, just assume that all the variables are local and we just go ahead and do that analysis. Okay, that makes our life simpler. But in practice, when we are actually trying to build a live variable analysis module, you have to be careful about uh, whether a particular variable that you are arguing about, whether it's a local variable or a global variable. I wanted to make one more point here, but I forgot what it is. Anyway, so this is, I hope in this lecture you got intuition about three different problems that we have seen. One is constant propagation, the other is available expressions analysis, the third one is live variable analysis. And we looked at different examples to get good intuition about the nature of data flow analysis problems. And in the next class, we will see how we can go about designing algorithms to solve these analysis problems. So that's all I have for today's lecture. In the next lecture, we will start with the analysis. We will look at the analysis algorithms for available expressions and live variables. And the analysis algorithms for these two problems, they have very different flavor, and comparing and contrasting these two different flavors, it gives you a lot of insight and intuition into these data flow analysis problems. So that's all I have for today. So I will see you in the next class. If you have any questions, you can ask me now.